Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this is the next video in our series about the analysis of variance, or ANOVA. More specifically, a two-way ANOVA with replication. This is also called a two-factor ANOVA. Now, to make the topic more manageable, I have divided the video into several parts. Here in part 1, we will discuss the conceptual background using graphics and charts while working through an example. And just a word of caution, this topic is not easy. You may have to pause, rewind, or rewatch parts of the video to let the information sink in. You must have patience and remain determined to learn. So in our last video, we took an in-depth look at the two-way ANOVA without replication and what it offers us. In a two-way ANOVA with replication, we have multiple measurements per cell, not just a single one. This allows for a new type of measurement, the interaction between two factors. So this video is very comprehensive. Here in part 1, I will use several illustrations to make concrete the abstract concepts underlying the two-way ANOVA with replication. In later parts, we will explore the two-factor ANOVA in more depth. So this video offers a solid, comprehensive conceptual foundation of two-way ANOVA and interactions using an example problem with illustrations and graphics. So if you are new to ANOVA or are still trying to figure out exactly what it is, this video is for you. So sit back, relax, and let's go ahead and get to work. So as with many of my videos, I love starting out with a real-world example problem. And we'll call this one Plant Food Research. And it goes like this. You are a researcher interested in the effectiveness of 3 different cotton plant foods. So Awesome Advantage, which will denote AA, Big Buds, which will be BB, and Copious Cotton, or CC. Therefore, you design an experiment in which you will test each plant food, AA, BB, and CC, with 1 feeding per day for 75 days after planting. 8 plants will be tested for each combination. The variable of interest is the plant height in centimeters. So, we're going to take each plant food, AA, BB, and CC, we're going to put 8 plants with each food, and we're going to feed it once per day for 75 days, and then measure the height of the plant. That's our experiment. Now, the same type of cotton seed will be used for the entire experiment to control for the type of seed. Here are our results. So you can see that we have 8 plants in each cell. So AA has 8 plants, 8 measurements, BB has 8, and CC has 8. Now on the left you can see that we have 1 feeding per day. Now technically we don't even need that over there because we only have 1 factor on the left hand side, but you can see we have 3 factors along the columns. So each column, each food type has its own mean. So plant food AA had a mean height of 60 centimeters. Food BB had a mean height of 62.5 centimeters. And food CC had a mean height of 57.5 centimeters. So what we've done here is a one-way ANOVA. We've only analyzed one factor, which is the different types of plant food. And what we're asking, remember, in a one-way ANOVA is there a difference in heights among these 3 foods? So we have AA at 60 centimeters, BB at 62.5 centimeters, and CC at 57.5. And the one-way ANOVA allows us to test more than 2 means. Now when we go ahead and do that analysis in SPSS, this is what we get. We get an F statistic, or an F ratio, of 1.167, which is pretty low. And you can tell by the significance level of 0.331 that it is not significant. Remember, we're looking for a significance level of 0.05 or lower. So this is not a significant result. So in this case, our null hypothesis states that there are no differences among the plant food means based on the 1 feeding per day. So based on our results here, we failed to reject that null hypothesis. That's another way of saying there is no evidence that the plant food growth means differ in any significant way. So remember, I think we had a mean of 60, a mean of 62.5, and a mean of 57.5. So those are all pretty close together. So there was no significant difference among them. So in the real world then, based on this one-way ANOVA, where we're only looking at plant food type, we could make our plant food decision based on some other criteria. Because based on growth, it doesn't really matter which one we use. So we may use the one that's cost the less, the cheapest. We may use one that has the less environmental impact, etc. But growth alone is not a deciding factor in what food to use based on the results of our one-way ANOVA. So now let's look at a 2-factor model for plant food. So we had a one-way ANOVA in the previous one. Now we're going to do a 2-factor or two-way ANOVA. So let's assume that the plant food is relatively inexpensive and 2 feedings per day are possible instead of 1, while still remaining in budget. So let's stop and figure out what we are asking here if we do this. Now we already learned that plant food alone does not impact plant growth when given at 1 feeding per day. So our one-way ANOVA, just looking at plant food for 1 feeding per day, was not significant. Now we're going to ask, is there any difference in plant growth when comparing 1 feeding to 2 feedings per day? So we're going to have another factor, and that is the feeding frequency. So our last question, and this is hinting at the concept of an interaction, is do some plant foods work better once per day while others work better at twice per day? So feeding frequency together with food type. And we'll learn more about that here in a few minutes. Let's go ahead and do this experiment. So here is our data. Now the top 4 rows are the exact same as we had before. So we have our 3 plant foods, AA, BB, and CC, and then we have the 1 feeding factor here on the left. So all those numbers are the same. But now we added another factor, the 2 feeding frequency. So now we have more data to work with. So you can see that I have AA in all red, BB in all blue, CC in all green, and then for the 1 feeding is in a gray color, and then the 2 feeding is sort of a brown color. So you can see each column and each row. So we have 6 sets of 8 plants in this experiment. So we now have a 2-factor or 2-way ANOVA with replication. And it's with replication because each food and feeding frequency has 8 plants. So there are 8 plants in AA1, 8 plants in BB1 feeding, etc. So each cell actually has its own mean and variance. And this is very, very important for understanding the fundamental concept of the two-way ANOVA with replication. Each cell, since in this case it has 8 plants, there will be a mean and a variance that goes with each cell's 8 plants, more specifically. So for AA, remember we had a mean of 60. So those 8 plants in that combination have a mean of 60. For BB, those 8 plants were 62.5. And again, these numbers are the same from our one-way ANOVA earlier. For CC, we had a mean for those 8 plants of 57.5 centimeters. Now, for the 2 feedings, for food AA, we had a mean of 67 centimeters. For BB at 2 feedings, we also had a mean of 67 centimeters. And for 2 feedings at food CC, we had a mean of 40.5 centimeters. So as you can see, each cell is comprised of 8 plant measurements, so each cell has its own mean and variance. And that's very important to keep in mind as we go. So excuse all the colors, I'm just trying to use them to point out what is what. So here we have our cell means. So X bar AA1, all that means is food AA with 1 feeding is 60. Then we have 62.5 going over, then 57.5. And then below that, we have AA2. So 67 centimeters, and then go over 67 centimeters, go over again, 40.5. That's the same thing from the previous slide. Now what I've gone ahead and done here is added the means for the columns and the rows. So let's actually just take a look at this chart, because it's really important to figuring out what happens later when we do the analysis. So let's look at the column means. So for AA, BB, and CC. So for AA, we have a column mean of 63.5. How many plants does that comprise of? Well, 8 plants in AA1 and 8 plants in AA2 feedings. So 16 plants. So the 63.5 is the 16 plants that were all fed using food AA. Now go over to BB. We have 64.75. So again, here, all 16 plants, whether they were fed once or twice, are in that mean. So 64.75. Now go over to CC. So all 16 plants that got food CC, 1 and 2 feedings, had a mean of 49. Now if you look at those 3 means, what kind of stands out to you? What should sort of stand out that the mean for CC is significantly lower than the means for AA and BB. So keep that in the back of your mind as we go. Now I'll look at the means for both rows. So we have the 1 feeding row and the 2 feeding row. So the mean for the 1 feeding row is 60 centimeters. For the 2 feeding row, it's 58.17 centimeters. Now, how different are those? Well, those aren't very different, are they? They're pretty close together. So if we look at the columns, which is the food type, we can see that CC is kind of the oddball at 49 centimeters. If we look at the rows, the feeding frequency, the 60 and the 58.17 are actually pretty close. Now if you look at the relationship between those to the overall mean of 59.09, you can see how those means relate to the overall mean. So the row means of 60 and 58.17 are pretty close to the overall mean of 59.09. And then as far as the food type, the 63.5 and 64.75 are a bit above, and the 49 is significantly below the overall mean of 59.09. So keep in the back of your mind, it's really important, the relationship between the row means of 60 and 58.17 and the column means of 63.5, 64.75, and 49. So it is very important to remember that when we make a table of means like this one, the values are not individual data points. They are all means with their own distribution. In a two-way ANOVA like this one with multiple measurements in a cell, the way the distributions fit together is at the very heart of the technique. So this is a big puzzle of distributions, and the way those distributions fit together is what makes this two-way ANOVA with replication what it is. So next, let's go ahead and plot the cell means on a graph. So this is the graph for our one feeding example, our one-way ANOVA. Now, a lot of students I work with get confused on how to set these up. So let me make it as simple as I can. Along the bottom in the x-axis, that's usually going to be the variable you're most interested in. So in this case, we are interested in the food type, food AA, BB, and CC. Some people say that you should put the variable with the most categories along the horizontal, and that's up to you, but we are interested in the food types. So that would be along the horizontal axis. Now on the left-hand side, the vertical axis or the y-axis, that is actually our dependent variable, or actually what we're measuring. So in this case, that is the height of the plant. So like the horizontal axis, we have the variable we're interested in most, in this case food. On the left-hand side, we have the dependent variable, or what we're actually measuring, which in this case is the height of the plant. So what we do is we plot the height of the plant for each food on this graph. So if you remember, for food AA, the mean was 60. So it's right there at the 60 mark, the red dot. For food BB, it was like 62.5. So that's the blue diamond there in the middle. And then for food CC, it was like 57 something. So that is there with the green diamond. So all we have is a chart of the measurement for each food. Now what about both feeding levels in the same graph? So this is with both factors. So sort of the grayish green line is the same one we had in the previous slide. That's the one feeding. Now if you look at the other one, that is the two feeding measurements. So for food AA, it was about 67. For food BB, it was 67. But then for food CC, it was down near 40. So you can see there's a drastic drop in plant height for food CC when we fed it twice per day. So the steep line there, that's the two feeding line, and then the more flat line is the one feeding line. So that's actually a table of marginal means. And this is the same output in SPSS. So it looks the exact same. So you can see the blue line is our one feeding per day, and the green line is our two feedings per day. So here are some questions to ask. For food AA, or awesome advantage, how many feedings produced more growth? Well, for AA, it was two feedings. You can see that the green line is above the blue for AA. What about for big buds, or BB? Same thing. The green line is above the blue one, so therefore there was more growth with two feedings for big buds. Now what about CC, or copious cotton? Well, in that case, there was more growth with only one feeding for that food versus two. So when we added a second feeding, the growth really went down. So the question we ask ourselves is, do two feedings produce more growth across all plant food types consistently? Well, do they? Does it for AA? Yes. Does it for BB? Yes. Does it for CC? No, it does not. So, it appears no. It appears that two feedings are better for AA, but not for CC. This type of situation is called an interaction. An interaction occurs when the effect of one factor changes for different levels of the other factor. In this case, the most effective feeding frequency changes across plant food types. So for AA, two feedings are the best. For big buds, two feedings are the best. But when we get the copious cotton, it changes. Now one feeding is the best. And that's what we mean by an interaction. So on a marginal means graph like this, as a general rule, we look to see if the lines cross, or if they would cross. Now, that's sort of a conjecture. If they cross, they cross. But if they would cross, sometimes that's an interaction that is meaningful, sometimes it may not be. But if they cross, that's something we're really looking for. So this slide has a lot of information. So let's go take it one step at a time. So here is our table of our means. So you can see all of our cell means, our row means, our column means, and our overall mean. Here is our graph of marginal means. You actually look at this on the graph. So for one feeding per day, we have 60, 62.5, and the 57.5. That's the blue line on the marginal means graph. For two feedings, we have 67, 67, and then 40.5. That's the green line on the marginal means graph. Now let's look at the actual output from SPSS. Now we're only interested in the output that's inside of this yellow box. SPSS gives us a lot more information than we actually need to do this type of problem. So you can see there we have three factors that we're looking at. We have feedings, which is the feeding frequency. That is the rows in our table down there. We have the plant food type. Those are the columns in our table at the bottom. And then we have this other one, feedings times or by plant food. And guess what that is? That's our interaction. So we're looking at three terms here. The frequency of feeding term, that's the top one. The plant food type term, that's the columns. And then we have the interaction, feedings by plant food. Now, look at the significance levels. For feedings, it's what? 0.451. Is that significant? No. Now look at the means in our table at the bottom. For one feeding, it's 60. For the two feedings, it's 58.17. Are those very different? No. That's why that factor in the SPSS output is not significant, because they're so close together. Now let's look at plant food. Is it significant? Yes. Why? Look at the means in the plant food. We have 63.5, 64.75, and 49. Well, you can tell that the 49 is really different than the other two. Now let's look at the interaction. Is it significant? Yes. Now look at our graph over here on the right. What happens? They cross. So two feedings is better for AA, two feedings is better for BB, but for CC it's way worse. So we have this interaction, and that is significant in our output. Now, when going over that, I just did commit a cardinal sin of interpreting a two-way ANOVA. You always look for a significant interaction first. So had you known this concept before, I would have gone over the interaction first. But we always look for a significant interaction first. And why is that? Well, if the interaction is significant, then we stop there. Why? Well, if the interaction is significant, it means the two individual factors are too intertwined. They are too tied together to look at them individually. So as soon as we have a significant interaction, we stop there, that's our result, and we do not look at the two main effects, that we call them, individually. And that's very important when doing your interpretation. Okay, so let's go ahead and go into Excel, and I'll show you really quickly how to do a two-factor ANOVA with replication. So remember, there are several ANOVAs in Excel, and we're going to be looking at the ANOVA two-factor with replication. So what we're going to do is I'm going to have the Excel file ready to go. I'm not going to show you how to do the hand calculation for a two-way ANOVA. That is insane to do that. So I'll have the data already set up, and I'll very quickly show you how to format it, how to select the proper data analysis selection here in this box, and then show you the results really quickly. So let's go ahead and go into Excel, do that, and then we'll come back and finish up the video. So here we are in Excel, and I'm going to quickly show you how to set up a two-factor ANOVA with replication in Excel, and then go ahead and conduct the analysis. So as you can see here, we have our three plant foods in the columns, AA, BB, and CC. On the left-hand side, we have our other factor, so one feeding and two feedings. Now, the way we do this in Excel is we work within columns. So the one feeding for AA, we're going to do those 8 measurements down the column. So 65, 70, 60, 60, 60, 55, 60, and 55. Then we do the same thing for one feeding in plant food BB. Those 8 plants. Then the same thing for one feeding in food CC. Those 8. Then we start a new section. Then we have 2 feedings. And then right next to it, we start the next set of measurements. So 2 feedings in plant food AA is 50, 55, 80, and so forth. Those 8 plants, 2 feedings in BB, those 8 plants, and then 2 feedings in CC, those 8 plants. And for the two-factor ANOVA with replication in Excel, it has to be set up just like this. So if we had 3 feedings, we would set up 3 feedings down here, like that, and then we would have 8 more plants for AA, 8 more plants for BB, and 8 more plants for CC. Okay? If we had a 4th plant food, say DD, we would have 8 of them for one feeding and 8 plants that get 2 feedings. So you can see how this is put together. Okay, so let's go ahead and actually run the Two-Way ANOVA with replication in Excel. So we'll go up to the Data tab in the ribbon. All the way to the right, we have Data Analysis. So we'll select that. Now we want the ANOVA two-factor with replication. Go ahead and click OK. Now for the input range, I'm going to go ahead and click the little box and select. Select the top left, even that empty cell, and select all your data with your column headings and your row factor headings there on the left. Go ahead and click back. Rows per sample. Well, how many plants do we have for each feeding? Well, we have 8. Type in 8. That tells Excel to start a new factor every 8 numbers. So alpha will leave at 0.05, and we'll send the output to a new worksheet. So we'll go ahead and click OK. And there we go. So I'm going to expand some of these columns out a bit. Okay. Now the important part is down here really at the bottom. So let me zoom in here. Scroll down. And here are our p-values. So the first thing I'm going to do here is just clean up the table a little bit. And I'm going to reduce some of these decimals down. So I'm going to go over here and we'll make them 3. Easier. Now we're interested in these cells right here, the F and the P value. And I can go ahead and give them a little bit of color so we can see them better. Like that. If you remember from our SPSS output, our feeding frequency F ratio was 0.578. Well, guess what it is here? 0.578. What the p-value was for the feeding frequency in SPSS, 0.451. Same thing here, 0.451. And the same thing holds true for the food types, so for the columns, remember that's the food type, is 16.526 for the F ratio, p-value 0.000. The interaction had an F ratio of 9.333, p-value 0.000. So, long way of saying, this is the exact same results we got from SPSS. So let's go back into PowerPoint and finish the video up. Okay, so we saw our Excel output, and let's compare that to our SPSS output we had from before. So here's our SPSS output, and remember, we're interested in the feedings term, the plant food term, and then the interaction term below that. So I have them highlighted in yellow and purple. Now here's our Excel output. So look at the information in the yellow boxes. For SPSS, we have feedings with an F of 0.578, a significance of 0.451. Go up to the Excel output, what do we have? We have an F of 0.58, a p-value of 0.45. They're the exact same, just one more digit is taken out of the Excel one. Now go to plant food. We have an F of 16.526 down at the bottom, significance of 0, 0, 0, go up to the top in Excel, 16.53 and 0.00, same. Now go down to the interaction at the bottom. We have an F of 9.333, significance of 0.000, go up to the Excel output, and what do we have? The same thing, 9.33 and a p-value of 0.00. We got the same output in SPSS and Excel, so we could use either one of the software packages to get a result. So a few final takeaways and then we're done. So in this type of ANOVA we have 1, 2 factors, and 2, multiple equal numbers of measurements for each factor combination. So this is called a balanced design. So if you remember, we had 8 plants in each cell. That's called a balanced design for this 2-factor ANOVA. Each cell of 8 plants in this case has its own mean and variance since it contains multiple measurements. Both the mean and the variance are important. Each factor level will also have its mean and variance. So if you remember, each row had its mean and variance, and each column had its mean and variance, and of course we had an overall mean and variance. A graph of marginal means is very helpful for visualizing the data. So the graph of marginal means is extremely helpful in your overall interpretation. On a marginal means graph, usually, the factor of interest or the factor with the most levels is on the horizontal or the x-axis along the bottom. The dependent variable is the vertical axis. This is what's being measured, so it's the y or the vertical axis. And then the second factor makes up the sort of series lines by graphing the dependent variable value for each level or category of the first factor. So if you want to go back and review those, you can, but I'm going to do the next video probably on just those interaction graphs. Look for crossing or non-parallel lines on the graph. If the lines cross, it almost always means there's an interaction there. Whether it's significant or not, you'll have to go ahead and do the analysis in Excel or SPSS or whatever. Now, non-parallel lines can also mean there's a significant interaction. You just have to do the analysis. But crossing is more indicative than non-parallel lines. In the output, always look for a significant interaction term first. That's always the first thing you do. If the interaction is significant, then the main factor's significance cannot be analyzed. The factors are too intertwined to look at separately. So always go for the interaction term first when you're looking at your F ratio and p-value or significance. Okay, so that wraps up part 1 of our video on the Two-Way ANOVA with replication. So I hope this gave you a fundamental, concrete foundation upon which you can gain further understanding of the Two-Way ANOVA. Again, using an example problem and several charts and graphs so you can see exactly what's going on sort of under the hood with this Two-Way ANOVA. So I look forward to seeing you again in our next video.